In this video, we're going to talk about what chemical equilibrium is. We'll derive the equilibrium quotient expression, and we'll talk about the difference between Q and K. There are some chemical reactions that tend to go to completion. By completion, we usually think of that meaning making products at 100% yield. So here's a good example of a chemical reaction that goes to completion. When methane combusts with oxygen, we get 100% CO2 and water, and there's no methane or oxygen left, or at least approximately none. This is one class of chemical reaction in which all reactants become products. There's another class of chemical reaction. In fact, most chemical reactions are not going 100% from reactants to products, but rather are a chemical equilibrium. An example of that, so we have N2O4 gas in equilibrium with 2NO2 gas. What you'll find is that whether you start with N2O4 or whether you start with NO2, you're going to end up with a reaction mixture that contains both of these. One of the biggest misconceptions about equilibrium is that people think that this is a pendulum kind of swinging back and forth, right? So sometimes we have NO2 and sometimes we have N2O4, and the pressures are constantly changing, or the amounts are constantly changing. That couldn't be further from reality. What equilibrium means, and we use this equilibrium arrow to represent it, is that while reactants are forming products, we call that the forward reaction, N2O4 going to 2NO2, that's your forward reaction. We also have 2NO2 going to N2O4. What's the equilibrium condition? Is that the rate of this happening are the same. So once we've reached equilibrium, we shouldn't see any change, so no more change in the concentrations or in the pressures. So let's look at some generic equilibrium. Let's say A plus 2B in equilibrium with C. So what we want to do is we want to write an equilibrium quotient expression. The equilibrium quotient is Q, and the expression is going to be the activity of C, which is the activity of the product, divided by the activity of A times the activity of B squared. Now I want to point out a couple of things. First and foremost, this squared is because of the coefficient. So A and C both have one stoichiometric coefficient, so the powers for those activities for A and C are 1. The second thing that I want to point out is that these are activities. Now, most chemistry books at the introductory level gloss over this, and they say, well, the activity depends on what we're talking about. If it's an aqueous solution, then the activity will just say that's equal to the molar concentration. That's if it's an aqueous solution. If it's a gas, we'll say that the activity is equal to the pressure of the gas. And if it's a pure solid or a pure liquid, then the activity is just 1. So let's give an example. Calcium carbonate solid in equilibrium with calcium oxide solid and CO2 gas. We would write the expression for the equilibrium quotient as the activity of CO2 times the activity of calcium oxide over the activity of calcium carbonate. Now these are both 1 because they're solids, and the activity of CO2 can just be the pressure of carbon dioxide. Let's do another example. For acid-base reactions, we have, let's say, acetic acid reacting with water in equilibrium with acetate and hydronium ion. So Q is going to be the activity of acetate times the activity of hydronium ion divided by the activity of acetic acid and the activity of water. Again, as a pure liquid, water is 1. And for all of these, I can use the molar concentrations. Here's a warning, though. These are approximations. In reality, these are not, the molar concentrations are not the activities, but rather the activity would be some constant, the activity coefficient, times the molar concentration. But since we're going to assume that we're dealing with ideal solutions, or solutions that are relatively dilute, we can assume that the activity coefficient is 1 and just set the molar concentration equal to the activity. So these are the equilibrium quotients, Q. So let's do one where we calculate some of these. So let's go back to a little bit of an easy example. A and B equilibrium with C. So what if I had, let's say, concentration, so 1 molar A, 2 molar B, and 3 molar C. So Q is C over A times B, and in this case it's 3 over 2 times 1, which is 1.5. That's great. The question is, what's going to happen? If I set up this situation, one of 3 things can happen. Either A, more products form, B, more reactants form, or it could be that there will be no change in the concentrations. So when will more reactants form? If we don't have enough reactants. When will more products form? If we don't have enough products. So the measure of the ratio of C, B, and A that's going to exist when this reaction reaches equilibrium is a fixed ratio, and that's called K, or the equilibrium constant. Let's pick a number. Let's say K is equal to 2. What that means is that at equilibrium, the ratio of C over B times A is going to be 2. No matter what the concentrations are, it will always be 2. So in the case that we were talking about above, where we have a Q of 1.5, Q is too small, meaning we don't have enough products, so more products will form. What if we had 0.2 molar A, 0.2 molar B, so let's see, concentration of A is equal to that, concentration of B is equal to that, and the concentration of C is equal to 0.8 molar. Well, if we do that, we can calculate Q for this, which is 0.8 over 0.2 times 0.2. And if we do that, we get 20. 20 is greater than K, right? This is greater than K. And if that's the case, then reactants are going to form. Okay, a couple of last examples and then we'll be done. What if, let's say, same K is equal to 2, we start with a 1 molar A, a 1 molar B, and 2 molar C. Well, if that's the case, Q is equal to 2, which is equal to K, and we're at equilibrium. Notice, though, we could have also started with 2 molar A, 1 molar B, and 4 molar C, and that would also have a Q of 2, which means we'd also still be at equilibrium. We could also have half of a molar of A, and 2 molar C, and 1 molar Sorry. And 1 molar of C and 1 molar of B. And Q would also be 2, which would also be equal to K, which means we'd also be at equilibrium. So there's a lesson in this, is that the concentrations aren't the same. Are not the same at equilibrium. Q is equal to K at equilibrium. Well, I hope this has been an interesting introduction to equilibrium. Stay tuned for more videos.